Days, yeah. Now we have Gustavo Alves. He's a student of Architecture. So his research is basically particle physics, but focused on any aspect of neutrinos. And then, from my understanding, you'll be joining Formula as a postdoc this year. Join the Northwestern.
Okay, thank you. So good afternoon, everybody. Thank you for having me here. Today I'll talk about our work called Chasing Serendipity, tackling transient sources with neutrino telescopes. This work is based on these two archive numbers, if you want to have a look, and was done in collaboration with Lua, Juber, Gabriel, and Renata. So let me start with what's probably the first question of the audience, which is, what is serendipity? If you look at the dictionary, you see that serendipity stands for the occurrence and development of events by chance in a happy or beneficial way, or an attitude for making desirable discoveries by accident. So by the end of this talk, I hope you understand why this is a fortunate and by chance happening. So let us start with now having a look at the remark of the title. If you may think that the motivation was multi-message astronomy, specifically the interplay between photons and neutrinos, but we actually asked ourselves the question whether neutrinos can be the only candidate to observe a given astrophysical source. And to answer this question, we will first, in the first part of this talk, we will be wearing our photon glasses, and I introduce how you can observe the universe through photons. For that, I need a few key concepts. We will start introducing the field of view of the different gamma ray observatories that we discussed. I'll introduce the coordinate systems that we are going to use, and I will briefly comment on the interactions that are relevant for these experiments that we are interested in. So, first thing is the field of view. Here I have a toy experiment, and the field of view is defined as the portion of the sky that the experiment monitors. Therefore, if I have a source that lies within the field of view of the experiment, the source emits a flux of particles, and if it's within the field of view, the experiment will probe this flux. However, Earth rotates, and this may change, and with time, this may be the case that the source now is outside the field of view, and the experiment will not monitor that source for a while. As a concrete example, let me show you what happens with a few gamma ray observatories. First, the working principle of these experiments is the following. Our Earth is bombarded by several particles called rays, gamma rays, and they interact with the Earth's atmosphere and produce a cascade of particles. We categorize these cascades depending on their content. So you can have cosmic rays and gamma rays interacting in the atmosphere and triggering cascades that are mainly composed by electrons, positons, and gamma rays. These are the electromagnetic cascades. We have also cascades that are mainly composed by hadrons, which are hadronic cascades. And we have cascades composed of muons, which are muonic cascades. The experiments we are interested in will measure the byproducts of these interactions at the ground level, and they can reconstruct the particle primary by looking at a few variables. So here I have an illustration of how this shower of particles looks like, and the relevant variables to reconstruct the primary interaction. So basically, they look at the number of particles, the maximum of the shower development, its muon content, and at the column of matter these showers have propagated through, and they can then view the likelihood and give you what are the chances of being a proton or a nucleus in the primary particle that triggered that cascade evolution. So here I have what is the instantaneous field of view. So basically that toy experiment that I showed, I had this cone, and here is that cone projected in a sky map. I will discuss all the experiments one by one, but this is how a snapshot of the instantaneous field of view of different gamma ray observatories look like. This sky map, for those who don't know, is written in equatorial coordinates, where we have the declination, which is sort of latitude in the sky map, and a longitude, which is the right ascension. The declination is usually measured in degrees and right ascension in hours, with 15 degrees representing 1 hour. For us, what is actually interesting for our main question is not the instantaneous field of view, but the instantaneous blind spots. These are these white areas that are instantaneously not monitored by gamma ray experience.
Well, there's satellite gamma ray experiments.
Yeah, we will get there. Depends on the energy range. We are focusing on the high energy tail, and that's why I'm showing just these guys. I will also comment on the effect of varying time soon, but here you can see that the colored region is for a fixed time stamp, and the dashed lines show 1 hour earlier, such that you can see that these regions will change with time. The instantaneous snapshot, they will move as we change the time, or if you want the right ascension. So let us break down the different experiments included here. We have HAWK. HAWK is, they have these several water tanks, and these particles that I discussed that are produced in the cascade, they enter these tanks and leave energy deposition there through radiation, and then they can reconstruct these variables that I comment and tell you what is the most likely particle to trigger that interaction. HAWK is optimized for the tens of GeV to hundreds of TeV energy range, and it's located in Mexico. In a similar class, we have LASSO in China, covering more or less the same energy range. In the higher energy tail, we have PRG in Argentina, which is optimized for the EV energy range. For those who are not used to these units, EV stands to 18 electron volts, so very high energy. And similar to PRG, we have telescope array in the US. We also
The SWGO will be more or less around the OG field of view.
I don't know. I think so, right?
Sorry, what was the question?
SWGO, I think so.
Yes, it takes,
Yeah.
it's, on the
Mhm.
right of the curve moment.
Yeah, I think so, yes.
Right, a bit of field,
Mhm.
I don't know. But it's not as big.
Yeah, it's not as big. Mhm. Yeah.
Not as big as OG.
Can I just ask a question? Any telescope that least, I mean, as I recall, any telescope, at least in the optical, or as you move along the year, they see different parts of the sky, they move in array, but they have a fixed deck. Now, I don't understand how this comes about because, you know, all of these observatories are fixed in some place of the Earth. So as the Earth moves around, what you see is a different, so this is correct in deck, but it cannot be correct in array. You're not seeing a fixed part of the sky at any given moment because the Earth rotates and then you see different parts of the sky.
Yes, but this is for fixed time.
Instantaneous.
Yes, exactly, instantaneous.
So, okay, but okay, just, so this, the array is irrelevant here. It's only the.
Okay,
difference
yeah,
between
yeah.
array and
Yes,
Right.
okay, yes. We also include in this plot Hess and Veritas. Hess is located in Namibia and Veritas in the US, but they work by a different principle in comparison to the other experiments because they actually collect the light, the particles that propagate through the atmosphere emit while propagating. So it's a different operational principle. And if you look at the plot, their field of view is also quite limited in comparison to the other experiments that will play a major role in the remainder of the talk. So, as I said, this is the instantaneous field of view. Now let us make what instantaneous means more precisely. Instantaneous means that I fixed this plot at a given time, and the time that I chose is the time at which this star was placed there, which was February 2023, the 13th, at 1 a.m., 16 minutes, 47 seconds. And this was the time where the chemistry-net event recorded what is the signal of the most energetic elementary particle ever observed. Here I have a video of that the collaboration made illustrating this event. This is the energy deposited by the muon that traveled through the chemistry-net detector. This is an immense energy deposition. And if you look at their paper, the muon was reconstructed to 120 PeV and 0.6 degrees above the horizon. And here,
Just remind me, the KM3 is Strings.
Yeah, strings in the Mediterranean Sea. Yes. Same work principle as ice cube, but in the sea. Here I have the matter profile of this neutrino and mu saw while propagating. If you, the black line is the reconstructed trajectory. The neutrino propagated through this black line and interacted at some point and produced a muon that made it to the detector. So this is an example of serendipity in practice because our work started before we came to that event. And after that result, we have a well-motivated time to fix those plots and actually a well-motivated location to look at in the sky. However, everything that I will discuss as general is not necessarily suited for the ChemTreeNet. You can do that for any source location and event in time that you want. And also, I was at the Neutrino 2024 conference, and I saw the announcement firsthand. So this is just a fun fact from a really career researcher that could experience this. And here I am in the background. In the front row, you have two Nobel Prize winners. And it was pretty nice to see the excitement in the room while this was announced. So just a fun fact. So the summary so far, we are wearing our photon glasses and we showed that there are instantaneous blind spots in the field of view of gamma ray experiments. But you may ask, why are we focusing on instantaneous field of view? Why are we not using these experiments at their fullest and look at how as Earth rotates, this changes? Why are we focusing on instantaneous time steps? Well, we can also call this event as the ultra high energy unknown in particle physics, because we basically have a clash of titans here. In the left-hand side, I have IceCube, which is a detector that is fully constructed and has been operating for 11 years. And in the right-hand side, I have ChemTreeNet, which is under construction. It will be like IceCube in the future, but right now, at the time of the event, it had at least 10% of the strings only operating. And how can one detect such a high energy event in ChemTreeNet and not in IceCube? If IceCube has been operating for a much longer time window, has a way bigger effective volume, and ChemTreeNet is just a new experiment under construction. Wait. So to answer this question, we first have to ask about the origin of this event. People have done that, and for a diffuse flux, if you compute the tension of not observing something in IceCube and observing one event in ChemTreeNet, this boils down to a 3.5 sigma tension. If you assume that this event is of a cosmogenic origin, the tension varies in between 3.1 and 3.6 sigma, depending on the flux you choose to model the cosmogenic flux. Here, let me make a pause for a shameless self-promotion that I have also working on the cosmogenic origin, and we have entertained the new physics possibility to enhance the high energy neutrino flux. We can discuss that in more detail if you want after the talk, but just a pause. Going back to business, we have also a transient origin where the tension is lower to sigma. Why does this tension goes down? This tension goes down because in principle, what makes the other tension so big is the fact that IceCube has been operating for 11 years and ChemTreeNet for like 300 days. For a transient signal, if it's a very fast transient signal, you are not playing against the IceCube whole lifetime, but just the duration of the burst. The 2 sigma I will explain in detail after we introduce the effective areas, because now what you have to model is the relative position of the detector and the source.
So when you transient here would be still like cosmogenic or diffuse, they could come in from anywhere still, right? In any position. So just can you remind us, maybe you did that again, the energies of the IceCube highest energy events, and they are comparable to the one in KM3 or
no?
Yeah. So you're comparing. How different are they? Are you making an assumption about the spectrum to make the comparison?
Okay, so
there are different energies.
Here is the diffuse spectrum fitted by IceCube. This is the ChemTreeNet event.
Okay.
Okay. And this is like the IceCube data. So the latest point, if I remember properly, is this one. So it's lower energies.
So
And
you're assuming one of these dashed lines that are going down, right? So for the
for the tensions,
for the rate of the higher energy events.
yes, for the tensions, yes, to compute these tensions, yes, that's what they are doing.
And it's a fit based on the model.
Yes. This is not what we did. This is this work that I'm citing here, but that's what they did. They work on the
Just an
hypothesis.
extrapolation. of
Exactly,
something.
yes.
That's an underlying model.
Exactly. So the K-internet event in that, if that's the case, it would be an upper statistical fluctuation of this diffuse.
But just to be sure, ice cube would be sensitive to those high energy events.
Should
if
be.
they were cosmogenic.
Should be.
Or-
That's where the tension lies. Exactly. Yes. So it's a very serendipitous scenario.
So, sorry.
Okay.
So if the rate is higher, it's an even bigger tension. So if I look at your plot, actually, it doesn't help us.
No, that paper does not address the tension.
No,
Yes, you're correct.
That plot
The
there.
tension would get worse.
You would, if you, yeah, the tension would get worse if you make the rate higher.
Okay, the idea of that paper is to actually, because if you look at the best fit of PROG of the cosmic ray composition, it's mainly heavy nuclei. And with heavy nuclei, you tend to produce lower energy neutrinos and lower here by the standards of these high energy events. So we just try to make a model where with the PLG best fit composition, you can still have some high energy neutrinos that would account for that, but that makes the tension worse. That's true. Okay. Okay, so going back to the transient sources help in alleviate the tension, as shown here. And for very fast transient signals, the instantaneous field of view, the relative position of source and experiment at the time, at the burst, during the burst duration is what matters. One example that I will discuss today is primordial black holes. Primordial black holes, I will just give you the key ingredients to follow the talk. Primordial black holes are black holes that hypothetically formed in the primordial universe. And because of the Hawking effect, they evaporate. And in this work, we assume that this evaporation process is into standard model particles, specifically photons and neutrinos. They do evaporate in all the particles, but we will focus on neutrinos and photons because these are the most likely candidates to make it to the Earth. These fluxes are composed by two components. You have a primary emission, which are the particles that are emitted directly from the PBH, and a secondary component that comes from the primary particles that were emitted from the PBH and then decay into photons and neutrinos. So for instance, pions.
You're still in thermal spectrum, of course.
Yes. The other thing you have to know here is the relation between mass and temperature. When the PBH is heavy, the temperature is low, but as it shrinks, the temperature goes up. Therefore, the final stage of the PBH lifetime will be characterized by a burst of particles at very high energies. And that's what's going to be key for our analysis. So here is now a more concrete example of a neutrino burst. In the y-axis here, I have the number of neutrinos emitted per energy and time. And in the x-axis, the energy of these neutrinos. And each line represents, each of these steep lines represent the situation tau b seconds or tau b time units before the PBH fully evaporates. So for instance, the blue line is 1 day before the evaporation, then 10 seconds, and then the minus 9 seconds. As you can see, as we move up, the flux of particles increases a lot, and the range of energies that you can reach also gets larger, such that during the 10 to minus 9 seconds, you will emit a bunch of particles going up to 10 to the 8 GeV.
So what are the assumptions? So you have primaries and secondaries neutrinos.
And only standard model.
Primaries are, of course, thermal. Secondaries are not thermal.
Yeah.
Right?
So here we are showing also the primary spectrum, which are these dotted lines. The secondary is the GeVs.
So the dotted lines are the thermal spectrum.
Yes. And we also show here the temperature, just a reference. It's not exactly perfect thermal because we have breakpoint factor, so the peak is shifted, but this is an illustration of the PBH temperature at the timestamp, the primary contribution, and the total spectrum. So the GeV is from the secondary.
Yeah, so just so that I place this in the context of the other acceleration mechanism for high energy particles, and typically what I remember is that they are you don't create a isotropic emission. It's very focused. In every case, it's like you create a beam line, typically with some small scale magnetic field, etc. Right? In this case, it's an isotropic
Yeah,
emission, right?
yes.
So it goes everywhere,
Mhm.
so it gets diluted everywhere.
Yes, we will compute the number of events, so.
So you need a distribution of binaural black holes that are, I mean,
Yes.
have to fit the size, their mass, so that they decay essentially now.
Yeah, I mean, we are not going to discuss the distribution. What we are assuming that the PBH we are looking for is one PBH nearby that would be drawn from a distribution.
How do you stop, because as you go closer to the operation time, the flux is going up, right? So how do you cut this?
The final stage is that once you hit the plus, everything, I don't know.
But that's the one that contributes the most, right?
Yeah, I mean, we stop the integration there. Yeah,
You stop at 1 month, okay.
if you find that out, publish.
No, yeah.
No, just.
Black Hawk is a code.
Yes, Blackhawk is the code we use it to generate these plots. Yes, it's pretty useful and easy to use. Okay, so now that we have discussed the PBH evaporation process briefly, and we have discussed the particles that we are mainly interested in, now we have to define some sort of instantaneous field of view of neutrino telescopes. Again, this is basically evaluating how the relative position of the PBH and the Earth changes with time. We start with IceCube. Why? Because IceCube has been operating for a while and we have public effective areas. So we have their actual reported effective areas, but IceCube is a detector located at the South Pole. This is a very privileged location because if you remember my sky map, the South Pole would be here, and then there is a symmetry there in right ascension. You can rotate everywhere and shouldn't matter for the source because IceCube in the South Pole. Therefore, every time you see an IceCube effective area, it's very likely that this was average over right ascension, and you only have the information about the declination and energy. For our case, as we need the instantaneous field of view, and as I will discuss, we need the effective area for several under construction and planned neutrino telescopes. We need the instantaneous information, so we have to engineer a way to put it back, this dependence on right ascension. To do that, we make use of the symmetry that IceCube is not dependent on right ascension, and we basically equally divide the effective area in several right ascension beams, and we normalize it in such a way that if you integrate over right ascension, we recover the nominal result. By doing that, I'm showing here the result for the effective area. In the y-axis, we have the declination, and in the x-axis, the energy. This is the effective area of IceCube after doing this protocol, and this is for the time of the K-net event. And as we can see, I mean, this star is exactly the coordinates of the event, and it lies within a region where the effective area of IceCube is not suppressed. That's where the 2 sigma tension comes from. In the right-hand side, I have the path through the neutrino would propagate in IceCube, and it's only 14-ish kilometers. That's, I mean, IceCube should have seen something. That's where the 2 sigma tension comes from.
So how come it is detectable in the Mediterranean and in IceCube with an almost vertical line? Is that line in order to represent the
Yes,
derived direction?
Mhm.
So
The plot is misleading because the Earth is not
Yeah.
Yes.
round, the plot.
Yeah.
Like it's distorted because of the scale, but it's almost always.
Yeah, horizontal.
Result.
oh,
Yeah.
the opposite. I thought it was
Yeah.
almost vertical.
Yeah.
So this depth is
Yeah,
No, it's correct, but
Yeah.
it's correct. It's just,
you rotate by 90 degrees, basically.
Okay, I see.
All right, thanks. Okay, then it makes sense.
yeah, I don't remember exactly the number, but it's pretty
I
close
mean,
to
it makes perfect sense because you're talking about 0, minus 90, and in the Mediterranean, it's pretty much like plus 30. So you're talking about 120 degrees of difference.
plus
Still, it makes sense.
plus 30.
Yeah, so
It's 0.6 degree above the
that is
horizon.
about 25, 30 in the Mediterranean, the KM39. So, and if you're in South Pole, that's minus 90. So it's like more than 110 degrees difference. Still, it's okay? I mean, it makes
Yeah.
sense.
Yes,
I mean-
the difference in ice cube, it came with 0.8 degrees, and in came to net, it came with like almost 8 degrees, so more or less than.
Yeah.
All right.
It was
okay.
0.6 degrees above the horizon, so it's not the same coordinate system that.
So it came right, it's okay, it wasn't on the, let's say, sweet spot for both.
You will see a very nice plot at the
Yeah,
end.
right.
Yes, serendipity. Okay, now that we have our effective area for ice cube, we have to find a way to get the effective area for the other experiments. And for that, I start with the source at the given location. And so I have a fixed delta and right ascension, and I will do a change of coordinates, basically. I choose a day, I choose a time, and you have formulas to actually rotate from the equatorial coordinates to local coordinates in the experiment. This is illustrated by this plot where we have the relation between declination and zenith for ice cube, which is always trivial because ice cube has no right ascension dependence, and for chemistry at the time of the event, which is the thick line, and for chemistry hours later, which is the dashed line. So as you can see, they reconstructed a local path that the neutrino will travel through the Earth will change because the relation between declination and zenith changes. And this means that, I mean, for ice cube, it doesn't matter, but for the other experiments, depending on when the event happens, things may become unlikely to be seen. So to get the effective area for other experiments, we work it under the assumption that all these neutrino telescopes will be like ice cube in the future. So we basically consider several ice cubes placed around the Earth, and we use the ice cube effective area to compute the local, the effective area of each experiment. By doing this change of coordinates, we find the local zeniths. We know the ice cube effective area in local zeniths, so we apply the same function for different zeniths, and we have a different result for all the experiments. And by doing that, we found the Kenznet effective area at the time of the event. And again, the event is placed in a place where it's likely to be seen, which makes sense. And here I have again the reconstructed path that, matches the one that I showed earlier from their Nature paper. But if you vary time, you see that, for instance, 10 hours later, the event will be quite unlikely to be measured by the chemical collaboration.
So for ice cube, this doesn't change because it's south pole, but for Chem3net, actually, so it doesn't change anything in there because of rotation. It means that ice cube is still fixed and it's not.
Exactly. Ice cube should have
So
seen.
just making things work. Right?
Yes, ice cube. Yeah, there is no time dependence for ice cube. Yes. So to make things more concrete, moving from the effective area to total number of events, now we have the propagated flux to the Earth. So we include, as Raul said, the penalty for anisotropic flux. So we have basically a factor of 4 pi d squared, where d is the distance from the source to the Earth. And then we integrate over energy, weighting by the effective area, and we integrate also during the burst duration. Actually, we integrate over tau b, and one may wonder what this tau b means. So just one detail before discussing that, I wrote there at Earth, just because for neutrinos to propagate them properly, you also have to take into account flavor oscillations. And this is a detail, but just to be precise.
Is this the cosmological distance in the end, or it can be more galactic? Or...
This is exactly what this is a free parameter right now. We will impose one event in chemistry.net to find the distance of the BBH.
So otherwise, if it's cosmological, you have to take into account expansion.
Exactly, yes. You'll see that. Yes. That's exactly. We will get there. Okay. So one may wonder what is the relevant tau b. And here, this is a tricky question that actually sparked very interesting discussions among us. And the caveat is the fact that, as I said, the final stage is characterized by this immense explosion of particles, such that if you integrate over the PBH lifetime and the final hundreds of seconds, what matters is the final hundreds of seconds. You get the same result. This can be illustrated by the simple formula where I have a relation between the PBH temperature and the time until it fully evaporates. And if you do the math, you find that during the final hundreds of seconds, the temperature is around V. And this gives you a naive idea of the typical energies that the particles that are being emitted will have. And if you want, if you lower the energy, you get like 15 years quite fast. If you go to 10 GeV, it's already 15 years. But as I said, the experiments we discussed earlier, they are optimized for this TeV energy range. And basically what will matter the most is the final seconds. That's why we have an instantaneous, the instantaneous field of view is what matters the most. So now comes the question, can the ChemTreeNet event be a PBH burst? We will start wearing your photon glasses again, because if you pay attention, you see that the star lies within the field of view of Hawk and the LG. If we start with Hawk, what's interesting is that we actually found in a hidden blog spot blog that by astronomers that Hawk was actually under mine test at the time of the event. But they have searched for gamma rays before and later, and they did not find any signal. I don't want to make like bold claims, but this kind of suggests some transient-like event, because they have not observed any gamma ray yet, and they searched for data before and after the event. And as I said, we also have the LG, but the LG, the energy threshold is very high. And for these energies, what really matters is the very, very, very final stage of the PBH lifetime, such that if you do the calculation for a PBH evaporating 10 to the minus 5 parsecs from the Earth, you would only have 0.5 events. So it's not crazy that they have missed such event. But there is a caveat. And the caveat is that, as I discussed, the distance matters a lot. What I said about the energy is true if you are within distances where the experiment is basically at the threshold of being sensitive. But if we want the ChemTreeNet event to be a PBH, we have to bring this PBH too close, such that LASSO, even though at the time of the final stage of the PBH evaporation, it was not, the event was not within LASSO's field of view, it would be hours earlier, and LASSO would act like a pre-burst monitor. Let us break this down. So the ChemTreeNet event basically was detected by the ARCA detector that is optimized for hundreds of TeV. That means we are talking about the last 100 seconds. And as I said, ChemTreeNet is not fully assembled. That means you have a penalty in the effective area too. If you combine these factors, the distance goes to 10 to the minus 5 per second, which is pretty close to the Earth. If you do that, you can look at earlier times, and you see that the event will be, the source will be within LASSO's field of view 14 hours before the PBH fully evaporates. And at this distance, just to give you an idea, these gamma ray experiments, they usually report bounds on PBH, and they go up to distance to 10 to the minus 2 parsec. So 10 to the minus 5 is way closer than their sensitivity. That's why they would see like 10 to the 5 to 10 to the 7 events. An immense amount of gamma ray would be deposited in these detectors 14 hours before the PBH final stages. We also show here how that one day before should have seen such a gamma ray signal, again, around 10 to the 7 event-ish. We don't know if it was operation at the time, but that would be the event profile. That means if you force one event in ChemTreeNet with this original setup at the time of the detection, it's quite unlikely that the PBH origin may be behind that. Was there any counterpart detected? Luana, not that I know of. I don't think there are any gamma rays that were detected from this event. So we are back to square one. Can neutrinos be the only candidate to observe a source? Now let me discuss in more detail what may happen. And here, I mean, I'm no expert on that. So if there are more things that may happen with gamma rays, I would be happy to know. But at least I learned during this work that they can be trapped or attenuated. So they may be trapped within the source, depending on the source composition. Or their energy may shift towards a lower energy range, and the correlation between the neutrino energy and gamma ray energy may be non-trivial. There were also works showing that the observation of chemistry may be accompanied by a delayed gamma ray signal, because now the sources are far away and the photons may interact in the intergalactic medium, and they can arrive up to 2 years after the event, for example, depending on the conditions you assume for the intergalactic medium. And the last option, which kind of, if that happens to be the case, if the source is outside the field of view at all times, then the other options doesn't matter, they don't matter. And we'll try to see if for a PBH, we can find any region where this is the case, considering the observatories that I discussed earlier. So now let us put our neutrino glasses on. And we have this plot, which is, again, our sky map. The gray regions now indicate the regions where LASSO and HAWK would cover varying for a day, so that they would cover that entire region, because, as I said, for LASSO and HAWK, if it's a PBH, it doesn't matter if it's the instantaneous or not, because they would act as a pre-burst monitors. So I'm taking out all this gray area, and as I commented, the PRG, only the effective, the instantaneous field of view is what matters. Therefore, I'm showing here just the field of view at the time of the event. That means we are left with a tiny white window here, where hopefully only neutrino telescopes could probe signals at this energy range. For this time window, we did compute the number of events for 7 neutrino telescopes. The under construction ICTP Gen 2, CambridgeNet and Baikal, and the planet P1 and Trident. Here in the x-axis, I have the declination of the PBH. This is excluded, as I showed in the from the previous slide. And here I have the number of events. As I said, we are assuming that all these detectors, when fully constructed, that they will look like IceCube, but we have corrected for the volume. So IceCube Gen 2 and Trident will have like 7 times IceCube's volume at the present conditions. And what's interesting is that if you look at this declination band, and as we commented, IceCube, here we fix the declination to, the right station to 300 degrees, but for IceCube it doesn't matter. And if you look, IceCube will not collect events in this band. The effect here there is suppressive. Therefore, if there is a source within this white region, we need the other neutrino telescopes. So here, just to give you an idea, for the distances we considered, it would be around hundreds of events for detectors that are exactly like IceCube, and for Trident, we would have this spike because it's 7 times the current IceCube volume. If the source lies within this region, we also attempted to perform a triangulation of the source. So basically, with muon tracks, these telescopes may use the directional information and the difference in time of arrivals to perform a triangulation and point to the sky, and they could locate a source. So here, the crosses show our benchmark scenario, and the colored ellipses show the 1 sigma, 2 sigma, and 3 sigma bands of the localization of the source. And here I'm varying time, so you can see the effect of the instantaneous field of view of PRG rotating with the time. And you can see that the shape of these ellipses also change because the relative position between the neutrino telescopes and the source changes as time changes. So the amount of events each collect individually changes, so their relevance for the triangulation changes. We need at least 4 detectors to properly localize the source without any degeneracy. So going toward the conclusions, what did we learn today? We learned a bit about the interplay between the field of view and the source position, and how important it is specifically for bursts of sources that emit particles within a very limited time window to model the relative position between the detector and the source properly. And by doing that, we learned that the Cambridge-Net event cannot be a PBH because it would have to be very close to the Earth, such that it's very unlikely that photon experiments will miss that. We also learned that neutrinos may be the only candidate if the event lies within that white region where that goes unmonitored by the gamma ray experiments. But it's important to emphasize the need of synergies to properly model the whole sky simultaneously. So we would actually like to be wearing these glasses where we can see both gamma ray and neutrinos to provide a full sky coverage simultaneously at all times. And here I have, as a summary, the big players of stock. We have Hawk, Lasso, and now I included IceCube and CandiNet bands. These bands are defined as the peak of the effective area of each experiment, so the most likely place for a source to be detected, and we vary 25% around it. That's why we have a band. And as you can see, and as Raul indicated, the event lies at the confluence of IceCube and CandiNet, and also within the field of view of Hawk. I think this event nicely illustrates a synergy of different experiments and also the need of having more neutrino telescopes. As we said, IceCube will not detect events where in the region where neutrino telescopes, neutrinos are the only option to probe a source. So this speaks for the need of having several neutrino telescopes to cover the sky map entirely and simultaneous. And maybe we can learn more now that we have entered in this previously uncharted territory that CandiNet has opened for us now. And that's it. Thank you.
Thanks, Gustavo, for this very intriguing. So any more questions?
So PBHs are, from what I understood, like they are excluded because of Lasso, right? Because they would emit photons before, for a long time before, and then Lasso would exclude them. So could it be another transient source that doesn't emit before? Just like a, I don't know, it's 10 to the minus 4 parsecs, hard to think of something like that, but some weird thing.
Yeah, so first thing, as Rogério pointed out, we did not comment on, for instance, Kremlin, which is lower and covers a lower energy range and has a limited field of view in comparison to the Earth-based experience. But for these distances, we could not include Kremlin here because it's very hard to find where it was, and actually all is here. But as Lasso already excluded the PBH, we did not look at Kremlin, but we would have also to look if you go to distance that close to all the gamma ray experiments that exist. But now, as I said, when I discussed what may happen with gamma rays, that list of paper shows sources that the neutrinos are the particles that are preferentially emitted. And in that case, you would have a source that is far away and emit only neutrinos, and then you have to do the whole business for that source.
But photons will be very high if it's that close. Photons
will be. I mean, neutrinos interact very little, so
yes,
photons interact all the time.
So, but let's say eventually when TF3net this explanation can still be consistent with statistical fluctuation, no?
Yeah, 3.5 sigma tension. It could be an upward fluctuation.
The flux at certain days.
Yeah, it could be a statistical fluctuation.
Gustavo.